So here we can see that we're doing example 20. Here I'm writing out the probability of getting heads on the first toss, and our sample space is above. The probability of uh, getting tails on the second toss, we see right there it's 1/2, and seeing the tails on both, which is 1/4 of a chance right there. So now A is asking, what is the probability of B given C? So we have the formula right there, which is equal to the probability of two t's, which is 1/4, and that is equal to 1/4. Oh, my bad, just one. So here we have part B, which is what is the probability of B given A? So here we have probability of B given A, which is the probability of B and A over the probability of A. And then we can write this out as 1/4 over 1/2, which gets reduced to, yes, there you go, yep, 1/2. There you go. For C, it says, what can we say about the relationship between A, B, C, or the probability of these events? So here we have is if the probability of B given C is equal to the probability of B, then we can say that B and C are independent. If the probability of B given C doesn't equal the probability of B, we can say that B and C are not independent. So we got to keep this in mind. Move on to example 21. It says you draw two cards from a standard deck of 52 cards without replacing the first one before drawing the second. Are the outcomes of the two cards independent? No. Why? Because when you draw two cards and you don't replace them, they can't be independent without drawing the second one. So I pick one, I have 52. I picked one out of 52. If I pick the second one, that's 1 out of 51 cards in total. Now we can move on to 2. It says find the probability of king on the first card and ace on the second. So this is the probability of K and A, which is equal to the probability of K times the probability of A given K. We know the probability of K, which is kings. There are 4 kings out of 52 cards. And then ace, there's also 4 aces, but remember, this is without replacement. Right over here. So it's 4 over 51. That is equal to 16 over 2,652, which gets reduced to 4 over 663. Now we can move on to number 3. Find the probability of drawing an ace and a king in either order. So this is basically the probability of A and K union the probability of K and A. This is intersection. So this is pretty straightforward. So we can say that's either king, ace, or king. So we can use the equation from the last problem, A and K, which is 4 over 663 plus another 4 over 663, which is equal to 8 over 663. Move on to example 22. It says the application to electrical systems. An electrical system consists of 4 components. The system works if components A and B work and either of components C or D work, which is, the diagram below. Now it says the reliability probability of working of each individual component is shown in the diagram so that the probability of A works is given by probability of A is equal to 0.9. The probability of that B works is given by probability of B is equal to 0.9. The probability that C works, the probability of C or D works is 0.8. So it says that assume that 4 components work independently. Now we're going to look at 2 questions that they're going to ask. So here we have part A, which is find the probability that the entire system works. So for the entire system to work, A and B work and either C or D. So we see that the probability of A and B and C or D, which is equal to the probability of A times the probability of B times the probability of B, C or D, right? Right there. Because of independence, we could write that way. And then now we can rewrite this as probability of A times the probability of B times probability of C plus the probability of D minus the probability of C and D. If you write out the or, and then we can continue on and we get probability of A times probability of B times the probability of C plus the probability of D times the probability of C times the probability of D because of independence. Now after that we can plug in the values. So A and B are both 0.9 from the equation, and then C and D is 0.8. So we can write 0.8 for where we see the probability of C and D, and then we can just do some basic algebra and we get 0.778. Now we can move on to part B, which is find the probability that the component C does not work given that the entire system works. So we can write this as the probability of C complement, which is not C, given that the system works, which is equal to the probability of C complement and system works over the probability of system works. Sorry. Which is we can say that this is equal to the probability of C complement and A and B and C or D, all over 0.778, because the probability of system works is 0.778 from part A. Now we can continue on and write this as the probability of A and B and C complement and D. Now, the way I got the numerator is we can have this because C complement and C or D equals C complement and C or C complement and D, which is equal to, you can't have C complement and C in the same event, so that's just the empty set or C complement and D, so we're just left off with just C complement and D. Just a side note, that's how we got the numerator. Now we can continue on by giving us, by independence, we would get the probability of A times the probability of B times the probability of C complement times the probability of D, all over 0.778. And then now we can finally plug in our values. So A is 0.9, B is 0.9 as well. C complement is 0.2 because C is just 0.8, and 0.8 minus 1 is just 0.2. And now we left off with the answer right there.